Okay, let's start. So let's discuss. Let's go ahead and discuss the article, and then I'm going to be, as you have questions and comments, I may be repeating a lot of that to make sure it gets into the video. So if that may get a little old, I just want to prepare you for that. That I'm going to be, if you're not in the other room, just want to make sure that the whole conversation makes the video. So, how did you like the article? Did you like it? So, what'd you say?
Even better the second time.
You read it twice?
Well, we read it last in Kristen's class.
Oh. We better work that out.
It's a good one.
My class was first. So I have dibs on this article. But what did you have an assignment relative to the article in that class?
Yeah, we did summary or I think it was
Pretty much this.
yeah.
Okay. Well, anyway, so for those who still worthwhile to talk about, and then there's probably has everyone read this before or no? No, half and half. Something like that. Okay. So there were two classrooms that they compared. So let's talk about the first classroom. So what kind of behaviors or how did what kind of characterized how the conversation went? So without comparing it to the other one, how can we just kind of generalize what that conversation was like, or what were the teacher and student behaviors in that conversation? And everyone's going to participate, so yes, ma'am.
I think it was like the first one. They were all about the numbers, like the specific numbers
Okay.
of the problem, and exactly what you had to do for that specific problem to get the answer.
Okay, so they were focused on numbers and getting an answer. Would you agree with that? Okay, cool. What else? Yeah.
I noticed that when a student got the wrong answer, so he just passed over it. So he didn't explain why it was wrong. How did you get the wrong answer? He just, that's wrong. Let's go to the next person.
Okay. So lacked explanation, especially when things were wrong. Okay, other comments? Yes, please. I'm still learning your name, so I want to have you say your name before you start talking.
Kendall.
Kendall.
Lacked direction, especially towards the end when the figurative long division was done. I used to check to see if it was the right answer.
Okay.
Yeah, with no direction.
So no direction. So did the teacher have a direction in mind when starting the conversation about?
Yeah, I think both of them did from starting, but then once it got into it, that was kind of lost.
Okay, so it kind of wandered off.
Yeah. Lauren.
Lauren.
And kind of going off that, it was so focused on how to do the long division instead of just focusing on what did it mean to do the long division. So it was very focused on it.
Focused on how to do it rather than what things meant. Okay, good. Other comments about the teacher or student behaviors and what characterized that discussion? One more?
I think when I first read the first one, I was like, am I going to be able to tell the difference? And then he started getting because I think at first he tried to say, oh, what is that number?
Mm-hmm.
But then it wasn't as deep as it should be,
Okay.
or as the second one was.
Okay.
So I think he was definitely at first at least trying a little bit, and
Okay.
then it just kind of didn't go the way it
Okay.
was meant to.
Yeah.
The first teacher wasn't as persistent. He kind of
Okay.
just gave up when they didn't
Okay.
get the answer.
All right. Less persistent. Good.
Jacob. There were relatively few students participating in the first week.
Okay. So that was focused on only a few students were chiming in. Okay. So a reaction I've had with classes in the past, and maybe you felt this too, was the students were saying while they were reading through that first vignette, they thought, hey, this teacher's doing a pretty good job.
Mm-hmm.
Did you feel like
Yeah.
feel like that too? Okay, so then moving to the second vignette. So what characterized the actions and of the teacher and the students and how that went? Tell me. Tamisha.
With the second one, I noticed it was more about what does that number represent.
Okay.
So they was more about the reasoning behind why they did it and what the representation of these certain numbers meant.
Okay, so you said two different things. You said reasoning of why you were doing things, and then the meanings of values. I thought I saw you next.
Genevieve, sorry.
Genevieve.
Something that was really interesting to me was the second one. At one point, the teacher was like, "Don't even worry about the number, like, because they were, oh, it's a third or it's 2/3 or whatever. Like, don't worry about it. Whatever it is, it's 5 years old." And then it was like just, so they were
Okay.
really not focused on even the number at all.
Okay. Not okay. Good. In the back. Tell me.
Jose.
Jose.
One of the, like somebody mentioned, one of the big things that stood out for me was like persistence. In the second vignette, like any time a student answered a question, the teacher would follow it up with another question, and even like stuff like there's one part where the student says a number and the teacher asks them, you know, what the units are, like what they're referring to, and so that was the big thing that came through me.
Persistence. Stuck with it. Okay. Meaning of that value.
Josh. And I was going to say, with that too, like through the questions that the teacher's asking, it involved more of a group activity of like understanding and involved in class and understanding the work.
Okay. So were more students involved in that second one? Yeah. Was there a greater number of students? Okay. So hand over here.
That's what I was gonna say. I think there were like 9 or 10 students involved, and they were also all helping each other, so they were all really engaged.
Okay. Tell me your name.
Angela.
Other comments? Yeah.
So going off, there's like at the end also, like all the students, the teacher had them recap everything that they did.
Okay.
Just to help them like solidify.
Okay.
What they.
So afterwards, summarize and review what happened. I saw you and then Daphne.
Yeah, I feel like in the
Tell me your name.
one, Ben.
Ben.
Sorry. I feel like with the second teacher, more students were able to contribute because if they didn't know the answer, there was still something they could add into it, right? You'd be like, oh, I know what units we're talking about. I may not know the end result, but that's okay. They could participate in the
Okay. Daphne.
Wanting to make sure that the students were explaining their understanding of the problem.
Okay.
Because she knew that a lot of them could do the computational work, but the teacher wanted to make sure that they knew why they were.
So they could do the computations? You're saying they could do them?
Well, they knew what to do with the problem, but the teacher wanted to make sure that they knew why they were doing those operations.
Okay. So they knew how to do the computations, but the teacher kept persisting on having them explain or make sure they knew why they were doing what they were doing. Good. Other comments? Yes.
I think the biggest thing that stood out to me is the teacher wanted to make sure everybody's on the same page. So every time somebody explained, does everybody understand that?
Okay.
Does not understand. So I thought everybody was following along.
So making sure that everyone was on board with the last thing that was said, following along. Tell me your name again. Bianca. Kendall?
Compared to the first one, instead of what does this number, or sorry, where did you get this number
Mhm.
from? The second teacher, what does this number mean?
Right.
Rather like abandon the number, what does this mean?
Okay, so yeah, the first one, focus on how do you get the number. Second one, focus on what does the number mean. Yeah, really good. Any last comments on vignette number 2? Okay. What else? So what were the discussion questions? So the question about the first question was about teaching as a cultural act. So had whatever external pressures on the first teacher, had those been removed? So what kinds of external pressures were we talking about? We're talking about like a department chair saying, we need to cover this material and you need to teach it in this way. Or a principal saying, we want our math education to be like this. Or the standardized tests driving how the teacher is going to teach. So these are all external kind of things in the immediate vicinity in time and in space around the teacher. Had all those been removed, would this teacher teach differently or the same? So the idea that teaching is a cultural act.
The way I kind of interpreted it was that like if that teacher, if that's how they understood how to do it, or if that's how they like grew up, doing their math, and that's carried over now to their teaching. No matter, you know, when people are saying, yeah, go for the calculation, they probably would do it that way anyways, because that's how they understood it, that's the only way they know how to explain it, and that makes sense to them. They don't see the benefit or drawback of it, or I guess they see more benefit than drawback to it.
But what if you just hand the teacher the Pathways curriculum? So is that gonna change the way they teach? What's going to determine how they teach? Is everyone familiar with the Pathways curriculum? It's this calculus. It's a very conceptually oriented pre-calculus curriculum was written here at ASU.
Yeah, what I had said is that like they mentioned in the paper that like it's hard to teach conceptually while also teaching to curriculum, and that's like one of the big difficulties of teaching conceptually.
Okay.
And so like it's tempting to say that the procedure, if we remove all the curriculum and like you said, the external pressures for people above them to teach a certain way, then maybe they would teach conceptually, but like probably not. Like we said, it's how he was taught to to do math, and so it's
Right. So does everyone know what it means? That means that the teaching is a cultural act. Can anyone just explain what that means? Teaching is a cultural act. What does that mean? Yeah.
We're affected by the way that our teachers taught us.
Okay. Yeah. So we grew up in a culture of a math education classroom. And so is that going to have influence on how we are as teachers? It's going to have the most influence. It's going to have the most influence. The types of experiences and the types of teaching that we're used to. So, so I think within a culture, you're just unaware that could be anything different. Right? So within a culture, you're unaware that there's anything different. This is just the way it is. But say in Japan, mathematics is taught very, very differently. And it's something we would never conceive of because of what it's been like for us in our experience. Tell me your name.
Oh yeah, I was gonna say I think people just get comfortable. Oh, Peters.
Peter. It's okay.
Either way.
Yeah.
So even if you taught just strictly calculational, if someone or conceptual and someone asks you to just teach calculational, you'd be very uncomfortable. So either way, like you just get comfortable in your ways, and you're probably not open to new ideas. But I think that's something as teachers we need to do is like continue to like grow and just learn different ways.
Right. So you said you get comfortable in your ways, and so the question is, where do those ways come from? Where do those ways come from? I mean, we've already kind of answered it.
Yeah.
Right? They come from, so they come from your image of what a math classroom is like, and that's from your 15, 20 years of being in math classrooms in your culture. Okay, what was the second question? How could you...
Explain how someone can have very good mathematical understanding and still teach with the calculation.
Okay, somebody new. So how could you have conceptual orientation but still teach with a calculational orientation? Somebody new? Shayna, do you have any comments on that one?
Yeah, I said that it's because it's easier. It honestly is. And that's how standardized testing is. That's how your PLCs are going to want to teach it. It's just simply easier. Like, you can have a deep knowledge in math, but to teach it to somebody else that deeply is hard. It really is.
Right.
So it's easy to get kids to point and chug, but to actually think it's hard.
Yeah, excellent. Tell me your name. Morgan.
I've had like teachers, especially at like college level, who they're so good at math that it's hard for them to understand that I don't understand. So they just teach it and they're like, oh yeah, because like when I learned it, it made sense. But for me, it's like I've never heard this concept before, so I don't get it. But they don't get it. I don't get it.
Okay. So so there's a difference just between having a really good understanding and then thinking about how do we transfer that. Ben.
Yeah. So I wrote that the tests we give to students generally only test on finding a solution and an answer real quick, and we consider that evidence of mastery.
Okay. So
what we do is we have them memorize without fully understanding. They produce an answer, and then we assume that they understand it and keep moving along.
Okay.
That's kind of where I saw how we wouldn't teach them the concepts if we think they fully understood it.
So what you're saying is that you could teach with a calculation orientation if that's all you're assessing, right? So if you really want to teach with a conceptual orientation, you've got to assess that. you've got to assess students' understanding, and just to have them do calculations and then assume that they understand it is you can't presume that. Tell me your name.
Chloe.
Chloe.
One thing I said was that like they might have like this really like deep understanding, but not have any experience teaching like conceptually, or like they've never had anyone teach conceptually to them, and so they might understand it like conceptually in their head, but like expressing that would be very difficult.
Yeah, that's really
They've
good.
not seen it before.
That's really good. Yep. Anybody else on this question? And then the last question was, be difficult to teach with a conceptual orientation if you didn't have the understanding yourself. Is that the premise of that one? So does somebody new want to chime in on that one? Yeah.
I just said that you would have to like, I feel like to understand anything conceptually, you would have to have like a really strong calculational background, because like you can't, like it's hard to, I don't know, like just because the way we've all been taught has been so calculational that it'd be hard to build on. I mean, but it'd be hard to build on that without having.
Tell me your name again, just say.
Oh.
Your name?
Me?
Yeah.
Sam.
Sam.
Sorry.
Okay. Sam. All right. So, why would it be hard to teach with a conceptual orientation without deep understanding yourself?
Well, my name is Joey.
Jody.
For example, if you're teaching a student and you're given like a book that tells you what to teach them, and you put a problem on the board and you show them that problem and how to do that certain problem, you're not going to know how to do problems that are similar, like have different numbers but like similar to that, because you have no like conceptual orientation how to actually do the problem. You just know the basics and how to calculate it. So, for example, if you had a student who had like different numbers, you wouldn't be able to explain how to do it for them.
Okay.
They struggle with it.
Other comments on this last question? Ben again.
I think it has to do with the way you teach conceptually. It's based on the questions, and you cannot predict what kind of questions students are going to ask. And when you go through calculationally, you can set up the lesson in a way and guide it. But with conceptual, the students have so many weird questions. If you don't fully understand it, you can't guide it back on the way you're teaching.
Back to Kendall.
So, like in summary, the first sentence that I wrote, if one does not have a full understanding of math themselves, and they will not be able to direct and answer questions in a way that will all students.
Yeah. So again, goes back to what we talked about on Tuesday from the syllabus quiz. Is that you're imparting to your students everything that you are, right? So all of your mathematical understanding is what you're passing on to your students. Your attitudes about math, that's what you're passing on to your students. So if you don't have the understanding yourself, it'd be very difficult for your students to acquire that type of depth of understanding if you don't have it. Yeah.
Genevieve, there was an example later in the article about the 4 students, and there was one about how one of the boys he knew how to do it calculationally, so he just did it, and then the other little boy, he didn't know how to do it calculationally, so he got into this orientation that math didn't make sense. It wasn't supposed to make sense, and I feel like a lot of students that I either grew up with went that way, and that's sad. And that's kind of part of what we're talking about is if the teacher can't articulate it the right way,
Okay.
then all these students get lost.
Okay, so then students get this notion if they can't do the procedural, the calculational part, that it can't make sense at all. So then if the teacher isn't there to explain why it makes sense, then they're lost. Yeah, that's good. Any last comments about the article? Oh, so my question is, why do we read this article in this class? Did that question cross your mind? So this is about so there wasn't really anything specifically about technology and visualization in this article. Why do we choose to read it in this class? Tell me your name.
Because Jessica.
Jessica.
So in order to create the visualizations that we want to, we have to have an understanding of the math to put in the graphing calculator.
Okay.
And so we ourselves need to understand it so we can show our students.
Okay.
And so for that to happen, we have to have a deep conceptual knowledge.
Good.
Of what's going
Yeah,
on.
that's one excellent point. So if we're going to create visualizations, we have to know the math that's going to create them. Okay. And so our own understanding is really important. What else?
I think also
And it doesn't just incidentally help them. This is the point of the visualizations. This is the reason for the visualization, is to bring understanding to a topic or to a concept. That's the whole point of it, right? So it's not that it just, we have something else in mind and then it happens to do that, but that is why we're bringing a visualization to a problem or to a concept to illuminate for students that concept, that understanding better. So that's what this whole course is about in terms of visualization, is about helping student understanding. Helping student understand. Okay, so try an experiment. Grade your own. Ready? Here we go. So I found six major kind of things that should be in your critical précis. Okay? Here we go. Now, so yes, you're going to grade it, but then you are going to turn it in, and I'm going to glance through them as I did with your quizzes, and some of you were a little too generous on number 2, the quiz on Tuesday. So you might have seen that your grade on Blackboard was lower than what you had given yourself. So if you want to see specifically why that happened, I'm more than happy to go over that with you. In fact, I can turn them back to you. But I'm going to review these, so listen carefully to how I'm asking you to assign points so that we can all do that accurately. Okay, here we go. So the first thing is that towards the beginning, you'd have to mention that this article is about 2 transcripts of 2 different classrooms. That there are these vignettes, 2 different classrooms discussing the same problem. And the article compared the transcripts of the 2 problems. Okay? So, if you didn't mention transcripts of class discussions comparing the same problems, that's a big problem. You kind of missed the whole point of the article. So, as long as you said that, 4 points. 4 points for that. That you said this article is about 2 transcripts of 2 classrooms doing the same problem and comparing what happened.
Sorry, I feel like there could be like a million questions. But if you put like, there's 2 main orientations that the article discusses, but you don't say specifically vignettes, is that like half or none?
Okay, yes, so half. But yeah, the article is about these transcripts, like comparing the transcripts in the classes, yeah. So yeah, you can take 2 for that. Okay, so the next thing in the article, after the vignettes themselves, there was a section on the behavioral differences of the discourse, like what we discussed, of the actions and discourse of the teachers' students. So they looked at the differences in behaviors in the 2 classes. 4 points. So you need to say something substantive, not just one sentence, but you're talking about the behavioral differences of the discourse and actions of the teachers and students in the 2 vignettes. 4 points. So here, I'll even show you. So there's vignette 1, vignette 2. So here on starting on page 5, about the vignettes and teachers, similarities and differences. So a summary of that section, looking at the actual actions, discourse, but not really analyzing it yet. Just noting what was different. Okay, 4 points for that. Then the crux of the paper. 2 contrasting orientations. So they talked about the actions of a conceptual orientation, and they listed them. And then they talked about the symptoms of a calculational orientation, and they listed them. Certainly would have to be in your critical précis, talking about this part. So the actions of a conceptual orientation and the symptoms of a calculational orientation. So at least a summary of each of those lists, if you didn't include the lists themselves. Okay? 4 points. For the whole thing. For this, this teacher's images of pedagogical tasks and goals. So actions of the conceptual, symptoms of the calculational. So either you rework those lists or you summarize both those lists. and that's worth 4 points. Okay, and then the next section you would talk about would be consequences. Consequences of calculational and conceptual orientation. Page 8. And then they brought up examples with Alicia, Betty, Carl, and Don. So Alicia, Betty, Carl, and Don takeaways from calculationally oriented discussion. Sorry, so the consequences of student orientations, the consequences of the teacher orientations, they're talking about student orientations as a consequence of teachers, so that's worth 4. And then these individual examples, student takeaways, worth 4. Alicia, Betty, Carl, and Don. If you talked about some examples with those students, 4 points. Yeah.
So is like summarizing the 2 lists of like behaviors and consequences of the
Uh-huh.
like,
Okay, wait a sec.
we have those listed like those specific questions that they have, or should we have like said they ask these kinds of questions?
Okay, which section are you talking about?
The one, yeah, the summarizing the 2 different orientations.
Of the teachers. The orientations of the teachers?
It was before like the one about like the 2 lists.
Okay, you guys don't start talking, please. I'm trying to listen to Morgan's question. So please don't talk. Thank you.
Like the symptoms of the calculational one and the computational one.
Oh, so it was after this.
I don't know. I don't know.
Okay, so the first thing was just mentioning that the thing had the vignette had vignettes. Okay, then the next part was the part number 2. Number 2 was the behavioral differences. What did the discourse and the actions look like in each case? Behavioral differences. Then the crux of the paper was the teacher orientations. There was a list of the actions of a conceptual teacher and the symptoms of a calculational teacher. That's number 3. So after that was then the consequences of teacher orientation for students. So consequences on students was the next one. Does that answer it?
Yeah.
Yeah. So that's number 4. And then number 5 was individual student examples. Alicia, Betty, Carl, and Don. So if you said something about those examples that they gave. That's number 5. And then finally, number 6 would be the author's obstacles and implications. And so this is what they talked about. So you need to mention what they talked about and not just it was your own summary of the article, okay? So they talked about wrestling with including solution techniques and procedures along with conceptual orientation. So when a teacher wants to teach conceptually, they wrestle with, now how do I then also teach how to do problems, how to do procedures? So that was a big part of that conclusion they talked about. And then the second part of that conclusion they talked about was using a traditional textbook or not, or how do you move away from traditional materials, textbooks, or do you abandon it, or other support structures? Those are the last 2 things they talked about. So wrestling with including calculational procedures along with the conceptual orientation, and then also the textbook. So that's number 6, obstacles and implications, worth 4 points. Question?
So, I think the 5th part that you're talking about with the 4 kids, do you want us to specifically mention their names?
As long as you talked about the specific details of them, I guess the name isn't important. But if you talked about specifically about those examples that they used, then it's okay. That you don't have to have the names. So that's 6 items, 4 points each. So you can total up your points, and that makes 24. But we'll make it out of 20, okay? Because I know that there's going to be some. This is a little tricky, right? So I'll give you some benefit for that, benefit of the doubt. So total up all your points on those 6 items, which you could have a maximum of 24, but we'll take it out of 20. Okay.
For the differences and similarities, I have 2 paragraphs, one describing how the first teacher did it, and then one describing the second teacher. Is that enough?
Oh, sure. Yeah, number 2, you mean? The second item?
Second
Sure,
part.
sure.
Okay.
Sure. Any other questions about grading? We'll see. It's an experiment. We'll see how it went. So give your score out of 20, but it could be as much as 24. And then you will get credit for answering the questions as well. So we're going to turn all this in. So just once you're set on your grades, so then just face down, make a stack in the middle. I'll come around later. So just quickly, I see a great value in writing a critical précis. Do you feel a great value in that, or not? So you're nodding your head. So what value did you see?
I think it made me notice a lot more and pay a lot more attention to what I was reading, since I have read a summary about it, rather than just reading through it and being like, oh, okay, that teacher did a better job.
Yeah, that's it. So if you need to write a good summary or a shortened version, it forces you to really understand what the article is saying. So do you feel that? Yeah. Okay. So yeah, and so this is a way to just hold you accountable, to not just reading it, but reading it critically and intently. So do you really understand what it said? Other comments on that? So if there's been some. In the past, there's been a feeling of it's not really helping me at all. But to me, I see it as really, if you really want to dig in and understand what the article's saying, having to write a long summary is going to really help you do that, from my point of view. Okay.
Will we have one of those each week?
No.
Oh,
We may have for at least one more, maybe 2 more. So we're not doing a lot of those. Okay. Here we go. So I'm going to ask you about. Before we get into this, how many people have had me or Owen Davis or Stacy Musgrave for calculus in this? You had me or Owen Davis or Stacy Musgrave for calculus. 1, 2, 3. Okay, so less than half. Okay. What I want to do in this course is, so I just want to kind of give you a heads up. At the beginning here, we're going to be learning the basics of GC. So we're going to be doing that. But then as we're doing that, we're kind of also, I'm going to kind of take you through, not a full version, but a version of a reduced version, but the goal is still the same, of the calculus course that I'm teaching, the Calc 1 course that I'm teaching. And it's Dr. Thompson and myself, he's the original author, and then I've been working with him on it for about 5 years now. So I've contributed much on it. And we just got a big grant. We just awarded a huge grant to further this project and to take a lot of data. And so it's a pretty significant redesign of calculus in the light of Pathways curriculum, or very conceptually oriented calculus. So I want, as much as we can in this class, we're going to be learning GC, and then we're going to be learning that as well. So you're going to be learning this this redesigned version of calculus that I've been teaching. So I think you'll really appreciate it. And so it may feel, and then the goal is then that they're going to merge, because as you get the basics down with GC and then you're understanding this calculus, then there's some of the assignments will be for you to be building the visualizations that I'm using in the calculus course. And as we know, to build these visualizations, you have to know the math, right? So this is going to be awesome. This is going to be great. All right, so let's start with talking about variables. What do you think when you see 2x minus 7 equals 0? What do you think? So, yeah.
Say a variable with one specific value that makes the equation true.
Okay. Which is? 7 halves. Okay. So when you look at that, do you see x equals 7 halves? Is that what you see?
I'm going to see the variable first.
Okay. All right. Could x be 4 or 10 or negative 0.5? Could x be 4? Could it be 4? Yes or no? Some saying yes, some saying no. So those saying yes. So someone, why do you say x could be 4? It's got to be 3.5, right? Ryan, is it Ryan? Okay, so he said x could be any value, it's just that 3.5 makes that statement true. So what if x were the number of hours elapsed since your plane left the ground? The exact same x that we're just talking about. What if its meaning was the number of hours elapsed since your plane left the ground, and 2x minus 7 equals 0? Okay? So now, does that change what you think about could x be 4? And what would x equals? Jose still doesn't like it.
Yeah,
So could x be 4, Jose?
Well, because in this situation, the numbers of hours elapsed since your plane left the ground, if like, I don't know how to explain it. I mean, it's true that x can be anything, but 3.5 is the value that makes it true.
Okay.
But in this situation, since we have this statement and like it is true and it is a real thing, then I think x can only be 3.5.
Okay. All right.
I think if you thought about units on 0, so maybe 3.5 hours after you've left the ground, your elevation is 0 feet above the ground. So like we didn't give x
Yikes.
a unit at first.
Did we land?
Yeah. We landed.
We landed. Okay. Phew.
Safely landed. So,
Okay.
So if you bring in more context for x, you can bring in more context for the rest of the equation too.
Okay.
And the numbers don't, you know what I mean? If 0 is like a different context.
Okay.
So
Sure.
going off of that, I'm thinking that now x can be anything 3.5 or less. Because if we've landed at 3.5, then we can be in the air.
That was his idea.
Okay.
That's still a specific context though. You just pick a new context. It can be greater than 3.5.
Right. Okay. So I think as a whole, I think we've got the idea that x can take on many values. And what about negative 0.5? Can x be negative 0.5 in this situation?
I mean, there is below sea level, which is a negative elevation.
Okay, but wait a second. What is x?
Yeah, wait, it's
Oh, it's gonna be like half an hour before the plane takes off, and you sit in there for a while.
How
before
many
you would
hours
leave the ground.
before it has
Yeah,
an
so
hour before you can
negative
do that.
values would just be hours before the plane takes off. So really, that's okay. So x could take on any real number. It's just that this 2x minus 7 is kind of pinpointing a particular value of x, but x is still taking on all the different values, right? So this idea that variables vary, right? Variables vary. And it's just, 2x minus 7, maybe this is like, this is an equation that tells us when we got our first snack or something like that. Ouch. Okay? So a variable is a letter or notation that represents the value of a changing quantity, okay? And this is where calculus begins. We have to see variables as taking on many values and progressing through those values, right? Changing through whatever values it can take on. Okay, so then just quickly, a constant is a non-changing value. A parameter, we use the term parameter to mean a letter that represents a constant, where a variable is a letter that represents a changing quantity. Okay, and then the domain is then all possible values that a variable can take on. So if a variable is changing, then the domain is all possible values the variable can take on. So just quick review. So let's take a look at something an animation that you're going to do something similar to, and it's good practice for this idea of parameters and variables. This one. Okay, so there are five letters or notations here: a, dx, left x, delta x, and x. Okay, and what we want to identify for each one of those, is it a variable? Is it symbols that represent a varying quantity, or is it a parameter, meaning it's a constant quantity? And then if it's a variable, what's the domain in this visualization? And then if it's a parameter, what is its constant value? Because parameters stand for constant values. So you can have a discussion at your table. And so let me just show you that delta x is showing the width or length of an interval of x. Do you see that? Dx likewise is showing the length or width of an interval of x, or a change in x. Okay. Left x is showing a particular value of x, as opposed to an interval of x. Does everyone see that? Okay, so discuss your tables, go through each one of these five. Okay, and so its value is, you said? 0.5. Everyone agree? Okay, next table over. Morgan, Jose, Josh, and Jordan. What did you guys say about dx? Dx
X is a variable.
Why do you say it's a variable?
It's always changing. The next left x.
Okay. And if it's a variable, it has a domain. So all possible values. What do you see as all possible values of dx?
I guess with any with any number, it changes from next left x to the next left x. I guess left x to left x plus.
Okay, so the lowest value of dx is left x?
For each. And then unless we want to go all the way over to.
But remember what I said about dx. What is dx? Okay, it's a variable, but remember I described it? It's a change. It's a width of an interval, right? It's or length of an interval, however you want to say it, width or length of an interval. So what's the lowest value of dx? It starts at 0, right? And then what's the highest value it has? Everyone see that? It's measuring how wide the interval is, or how long the interval is. It's not a measurement of the starting value of x. It's a measurement of so right now it's 0, and now it's increasing. The length of the blue arrow, right? The length of the blue arrow is the value of dx. Do you see it, Joey?
This really doesn't change anything, but with the constant value of a be 0.4, am I just saying it's wrong?
It's supposed to be 0.5. I think maybe it's an illusion because I've got some stuff over here. It's just making that look smaller. I don't know. But yeah, if you said it was 0.4, A plus still. A plus. Okay. All right. Are we good on dx? See, that's measuring a length. It's measuring an interval length or a change in x. Okay. This table up here. Tell me your name. Yeah. Shanley. Left x. What did you guys say about left x? Variable or parameter? Parameter. Variable. Is that your final answer?
No, they were somebody said, I said parameter.
So here it's simple idea. Is it a constant value, or does the value of left x change? Changes. Therefore, variable. Variables vary. Variables vary. It's a variable. Now, this is kind of a different. it's not a continuous variable, right? So if we look at the domain, we look at, so we're asking what values does it take on? What values does it take on? So I think 2 first, then 3.5. No, did I get that wrong? Then you could say it starts at 0.5. I think the animation, the first time in the animation, it's 2. But so that's why I wrote 2. But if you also included 0.5, that's okay. 5, 6.5, etc. I think the last one is 14.
First left X value.
Is it 2?
Yep.
Okay, so I have the list right. According to what you're seeing in the animation, the first one's 2, the last one's 14. So it's still a variable, but it's a different kind of variable than dx. Dx is this continuous, all values from 0 to 1.5, whereas left x is just these discrete values, but it's still a variable because it's changing in its value, right? Okay, next table. Tell me your name right there. Camry. How about, what did you guys talk about? Delta x. Parameter or variable?
Parameter.
So you're saying it's not changing. And so then what's its value? 1.5. So it moves, but it's a length or width of an interval, right? It's moving, it's in different places, but it's still that same length every time, 1.5. Are we good on that? Finally, x up here. Oscar.
So, well, originally we had said, well, it's a variable. Originally we had said negative 3 infinity, but in the animation it goes from 0 to continue on to.
So what is the lowest value of x just in the animation?
Oh, where it's stopping, where it's pointing. So 2.5.
Looks like it's starting at 2.5.
We're looking at the red line.
That's fine. That's all right. It's hard to see without stopping it. So it's as low as 2.5 and it's as high as? I think 14 here. And every value in between, right? Questions on this little exercise? So our goal is in a month or a couple weeks that we're going to kind of progress through the calculus and see lots of meaning in this. Lots of meaning in this, which a lot of it you may have an ideas about already. Okay, but this is just a kind of a foreshadowing of things to come, and then using this as an exercise to identify changing and constant quantities. Questions on that? Okay, so can we quickly, let's look at so this is Clara the calculus cow. And she is attached, she's attached to the silo. You're looking down on the silo, and the rope is attached here. And then the other end of the rope is attached where she is. And so the rope is just long enough for her to reach the east side if it was wrapped up around the top of the silo. See that? So then if she walks out, keeping the rope tight as she walks away, always keeping it taut or extended as much as it can, then there's this path that emerges that's like the boundary of where she could graze, okay? So this is the furthest she could get away if she wanted to graze around the silo. And then there's a fence here. Boom, electric fence. And so she's heading back. We love Clara. She's okay. All right, she's okay. It's low voltage, low voltage. All right, so here, this is an exercise now, and we've got this physical situation. How many variables and parameters can you come up with? Okay, so now here's a key thing about variable parameter. They're letters. So if you were to describe a quantity, and you don't attach a letter to it, it's just the quantity. It's not a variable or parameter. So if we're brainstorming on variables and parameters, that means you're assigning a letter to every one of them. You're assigning a letter to every one of them.
One of our parameters was capital R, which we said is the length of the rope.
And we'll say in meters. So length of the rope in meters, valid parameter in this situation?
Yes.
Unchanging quantity. Okay, good. What was your favorite variable? Or any of them?
Lowercase d
Okay.
was the distance that Clara has walked from her starting point.
Good.
In meters.
Is it specific? You know exactly what quantity he's talking about? And is that changing? Yeah. Changing quantity? Yeah, sure. Changing quantity. Okay, good. How about let's go back to this table. And Tamisha, what'd you guys, one of each? Anyone, doesn't matter. Doesn't matter, just pick one. A is the total area which she could graze in? And what about, oh wait, sorry. Yeah. Is that parameter or variable? Parameter, right? Total area she could graze in is parameter. There's some amount of area that she can reach, and that's not changing. How about variable, you guys?
That changes. She's got to move. She doesn't teleport.
Okay, and so is that time it takes to travel, is that a variable? Time since time since Clara started moving, is that a variable?
In seconds.
No, it has a variable.
It needs a letter. A variable is a letter. So T is the time Clara has spent walking from her starting point.
Yeah. It's seconds. Yeah, it's not that close.
Okay, we'll go with that. All right, so for time's sake, we won't go to every table, but is there anyone dying to share a parameter that they really liked? I don't want to leave anyone out. Or how about a variable? It's just variable, you just love that variable and you got to share it. Anybody? Yeah, Brian.
Why the distance Clara is from the fence?
Say y is and so are you seeing that as like a y coordinate?
Yeah.
Y is the distance Clara is from the fence. So that's always a straight distance down perpendicular to the axis. Meters. Sure, that's good. Part of her position, right? So this is not talking about position, right? This is one coordinate of her position as she walks. Okay. Questions on that? So that's just for fun, but you know the difference between variables and parameters. So let's talk about the homework, the GC homework. Any questions about this? Isn't that a cool animation?
Yeah.
You want to see the? Yeah. So I will be showing you how you. It's very easy. The cow is represented. That's a point. The end of that rope is a point that just has has a variable location, right? So as n changes, the location of the end of the rope changes, and so that command line where I graph that point, I just took the cow image from my Finder window and just drag and drop it onto that point, and then the cow appears on that point and moves with the point. So let me just let you onto something, right? So it's just, it has no idea what I'm displaying. It's just doing exactly what I'm telling it. I told it to graph a circle, and then I told it mathematically how to graph this It's actually in two pieces, right? That blue rope is going to be in two pieces. It's going to be the part that's wrapped and the part that's straight. Okay, so let's talk about your homework, the last one on your homework. Here. So that last question about what? The number of was it the remaining balance given so many payments, right? And given an interest rate. And so here I have that formula, B equals yada, yada, yada. And then here I have it as a function. Okay? So G of P, R, N, and M. And so here, this is a critically important question. And as it's what I've come to realize that students don't have a firm grasp of the answer to this question. So we should ask it. It's a really, really important question. What's the difference between a formula and a function? What's the difference between a formula and a function? Here's the formula version of that remaining balance. Here's the function version of that remaining balance. What's the difference between a formula and a function? Kendall has an idea. Okay, necessitates the need for an input or multiple inputs. Does the formula have that? Does it have input or multiple inputs? Does it? So multiple variables? What are you going to say?
Well, I was going to say they both have the same rule as like one of the formulas
Okay.
of the function, but with the function here, it allows you to kind of, represent kind of what Kendall was saying, represent different values for inputs without necessarily plugging it all the way back in the equation. Because with the first one, you can't represent, an input of, the rate of 0.05 without just plugging it into the equation. Whereas with the function, you can just say g of, and then yada.
You hear what she said? What did you hear her say? Somebody else. What did you hear her say? Someone else articulate that in your own words? So you should nod your head. What's your name again?
Melanie.
Melanie. What did you hear her say, Melanie?
So part of what she said is that with a function, you can use a function named g of whatever the input is to represent the output rather than having to find the output.
Okay. Other ideas?
It's
Is
like
it Peter?
Peter. There's a directional relationship for functions and not necessarily for the formula.
What do you mean by that?
Meaning, for the bottom one, you're going to need, you put in the principal rate, number of whatever, into that to get, well, I guess you don't have to. So that could represent the value. I guess define the value.
Sing.
I think as a function, you don't have to have the rule to represent like a potentiality with G with whatever the input is.
Okay.
As a formula, you have to have both sides.
Okay.
I think that a function doesn't have to be numeric at all. I mean, functions can represent anything in life where there's a unique output for each input. Formula, we're specifically dealing with numbers where you're plugging something in and putting something out.
Okay, so and that's the context I'm talking about. So in a context like this,
Oh, okay.
where you have a rule, you have a mathematical rule. So then in that case, what is the difference? So yeah, so this is really good. So look at what I've put here. So if I put, I gotta change this to A. So one thing in GC, if I define B here like this, and then I define a B again, it's gonna ignore this one. And it's just gonna take this one. You see? So I define B, and then I define it on another line B. So it's gonna ignore, it's gonna take the first one it comes to. It's gonna ignore this one. Yeah, once it's, if it's, so it's gonna, so what did it do? It just put one in. I didn't define any of those individual things, B, R, N, or M. So it just put one into all those and solved that. So I want it to show the real version of B, so I'm just gonna change this to A, okay? Does that make sense? No, turning it off is about graphing. It doesn't work. Okay, so what they were saying is absolutely right. If I want to represent a particular value of b, I need to write out the whole rule with everything in there. And then that will get me the value of b. Okay? But with function notation, this does great work for us, right? Because rather than write out this whole thing, what can I write instead? I can just use, this is the difference between a formula and a function is function notation. Function notation is this thing on the left here. It does very powerful work for us, like Kendall and Lauren were saying, that we can represent a particular value of output and know exactly which one we're talking about, right? By showing the particular values of input. Similarly to graph, right? Similarly to graph. So I can just write that I want my x to be number of payments, and then for these particular values of the other variables, and then that will graph then what's this remaining balance as a function of a number of payments made. But if I don't have function notation, I have to do this. I have to write out the formula with everything in it. So in calculus, we write lots of expressions that involve output values of functions. And it's really nice to know exactly which output value you're talking about in terms of according to a certain input. Right? Without that, our mathematics would start getting very messy and complicated and hard to read. So this is the beauty of function notation, and this is why function notation does so much work for us. Okay? So, in that light, this is a motorcycle travels through an intersection in miles as a function of the time elapsed since leaving the intersection in minutes. I'm going to name this relationship G. So when you saw that, what came to mind when you saw it? So everyone, think to yourself. Be honest. What came to mind when you saw G of 8.3? What does it mean? Okay, anyone want to offer up what you thought? Is it Jacob?
Distance.
You said a distance.
Distance from.
Uh,
A distance from the intersection. Yeah, should it be?
The distance from the intersection, 8.3 minutes after we left the intersection.
Okay, the distance, right, so it's the distance from the intersection, 8.3 minutes after leaving the intersection. Okay, so what this kind of notation, we want to see that this is the value of the dependent variable. In this case, a number of miles of a function whose name is G, when the independent variable has a value of 8.3. So another thing about functions is we've got this name. What is G? G represents this relationship between two quantities. You don't have that with a formula. You don't have a notation, so just the G by itself represents the whole function, everything about it, the relationship of the two quantities. All right, so one more like this. So here I got this. What came to mind when you saw that? What comes to mind when you see that? So did what came to mind, was it to do something? Did anyone think to do something? So some are nodding, right? Is that what it means, to do something?
Not initially.
It doesn't mean to do something. It means a value. Now, if you want to get that value, there's something you can do. Okay, but this doesn't mean to do something. I think that's how this function notation has really been framed in our curriculum. That it's commanding you to do something, to plug into and crank something out. When the reality of it is, it stands for a value whether you do anything or not. And if you want that value, then you can, yes, plug 2 in and get it. What, 18, 11. Okay, so you get 11. So that's how we want to we want to develop a really strong function mentality in this class, because calculus is utterly dependent on functions. So when you see notation like this, we want to see it as representing a value, first and foremost, representing a particular value of the dependent variable when the independent variable is that. And then if you have the rule, you can do something to get that value, right? To get that value. Okay, for homework on Tuesday, there is a packet, and it's a GC tutorial, and it's also about functions. So it's combining function understanding and knowledge with learning more about GC. You can work through that. I have office hours. You can email me questions, or I have office hours 9:30 to 11:30 Tuesday. The handwritten packet will be due Tuesday, and then there's also something you're creating on GC, which you will email to me. Okay? But all that detail will be on Blackboard.